Hi, welcome to lesson 3 in the series of 8051 programming and interfacing. You can also visit us at or for the web page for the same lesson at www.jcbrolabs.org. In our previous two lessons, we have talked about the internal architecture of the 8051 microcontroller and the internal architecture of RAM and various other functions. Now let's move forward, and now we'll talk about how to program a microcontroller, and especially we have a brief introduction about the programming language and especially assembly programming language for programming 8051 microcontroller. So if we talk about assembly programming language, so before assembly programming language, these assembly language are known as the low level programming language, because we write program as per the hardware instructions, like we access all the internal RAM locations, memory and various registers direct into the assembly programs. So hex file which is generated out of this assembly codes is being burned into the microcontroller. So these hex codes are nothing but just the numbers of zeros and ones. That means because microcontroller understand only binary language, so whatever code or whatever we write is a kind of 0 1 and 0 1. So we can write every time like this. So for making simple for normal users, we define this or we group these codes in terms of the mnemonics. So mnemonics are the instructions or English word letters which defines certain specific tasks, and each mnemonic is known as the a label of each mnemonic is the instruction, and a group of these mnemonics or the instruction makes a assembly program. So we have a structure of the assembly program, then it is label. Many times label is used to define, when we use jump instruction, and then mnemonic. Mnemonic is the English kind alphabetical letter like move, jump, JUMP, or you can say a call. All these are the mnemonic. Then there are two operations, are things like operand and then we can write like commands by writing this each command. So these operands are the registers or values on which this particular operation takes place. So the operand could be any registers, any memory locations, or any label. So these mnemonics defines like which kind of operation is going to take place, and these operands define at which this operation will take place. Like if it could be register 0, it could be register 1, it could be any memory location, say 85. So these are the operands. Like on 85 operation, move operation, on 85 location, move operation will take place. Or if we are writing move R0 R1, so R1 content will go into R0. So let's take an example of this code. So simplest example could be if we write like move R0 comma R1. So what is happening here? In this, the content of R0 will go into the content of R1. So these are the memory location of R0 as we have discussed in last lecture. So this is the memory 00 address of RAM, and this is the R1, so it is 01 address. So suppose here 30 is written there. So after this operation, this 30 will be copied into R0. So it will remain here and here as well. So 30 will be written as to memory locations at R0. So these are the memory locations and this is their content. So these are known as operand, and this is the mnemonic. Now moving forward, each instruction, and this makes a complete instruction for 8051 microcontroller. Now each instruction has some size as well as some time it takes to perform. So if we talk about the sizing pattern of this, like what could be the size, because ultimately this instruction is going to be stored in the microcontroller. So most of the instructions are of 2 bytes. That means 1 byte for this and 1 byte for storing the address of this R0 and R1. So these are 2 byte operations. Now each instruction takes some time, as we said, to execute. Now the time taken by the instruction to execute is determined in terms of the machine cycles. So now we'll talk about what exactly these machine cycles are. So, and this is very quite important topic when we talk about delays and other things as well. So we know we have applied an oscillator of frequency of F oscillator to the microcontroller. So when this oscillator goes into the microcontroller, so there is a clock circuitry inside it. That particular clock circuitry divides this oscillator frequency by 12, and the remaining frequencies comes in the clock. So as we know, all the internal peripherals or the devices of any microcontroller or digital device performs on the clock. So the clock frequency is known as the on which your microcontroller is working is known as the machine cycle. So the clock frequency for 8051 microcontroller is of simple formula, whatever you have F oscillator divided by 12. So suppose if you have a, let's take an example, if you have applied a 12 megahertz crystal across the microcontroller, so clock frequency will be of 1 megahertz. That means this kind of clock will be applied to the internal architecture, internal sub-peripherals of the microcontroller. So this is the frequency and this is the time period. So this time period, if we have a 12 megahertz oscillator frequency, so clock frequency is 1 megahertz. So the time period will be 1 microsecond. Simply 1 divided by 1 into 10 power 6, so 1 into 10 power minus 6 second. Now each instruction takes certain machine cycles to execute an instruction. So this is the machine cycles, and then suppose there is a move instruction, so it takes 2 machine cycles to execute, or I think it's take 1 machine cycle to execute the operation. That means the time taken by this move instruction is 1 microsecond. So within 1 microsecond it copies the data of register 0 to register 1. So it takes 1 machine cycle. So within 1 microsecond it transfers data from whatever operand are. Based on that, it takes on 1 machine cycle, and this also known as the instruction cycle. Like number of machine cycles taken by an instruction is known as the instruction cycle. Now moving forward, now we are working with this assembly language. So I think you are clear with this machine cycles. Now we will moving forward to the kind of instructions we could have in 8051 microcontroller, and this particular various kind of instructions are known as the addressing modes. Addressing modes means by how many various ways we can address or we can transfer data from one place to another place. So 8051 microcontroller have 5 kinds of addressing modes. That means it has 5 addressing mode, and we will talk one by one about them. So first addressing mode is the immediate addressing mode. IMMEDIATE. So immediate addressing mode. So in this particular addressing mode, particular data, now we will use two terms, address and the data. So in this particular addressing mode, any data is directly transferred into the any registers of the microcontroller. So if we write like move a comma hash 25. Now in assembly language, in 8051 assembly language, if we are writing this hash, then this hash is defined, it has defines like this next numeric value is the data. So what it will do, it will transfer this 25 data into accumulator. So this is the accumulator register. So the content of this accumulator will become 25. So this is the immediate addressing mode. That means the data is directly transferred into the register. So if we write like move R0 comma hash 30, so 30 will be directly transferred to the R0. So this is the immediate addressing mode. Then the second addressing mode which we have, that is the register addressing mode. In register addressing mode, the operands, both of the operands needs to be registers, like move a comma R0. So the content of the R0, whatever the content of R0 is there, that will transfer to the content of accumulator. So by this instruction, content of the register R0 will go into the accumulator. So in this case, both the operands are registers. Then it is known as the register addressing mode. Third addressing mode is the direct addressing mode. In the direct addressing mode, one of the operand is address of the memory. Okay, so in direct addressing mode, one of the operand is address of the memory location. So if we write like move a comma, let's take last example 25. So in previous we put a hash sign is there. If a hash sign is there, then it becomes a data, but if there is no hash sign, that it becomes a memory location, right? So if we write like this, move a comma 25, then the content of RAM location 25 will move into A. So this is the RAM location and this address is 25. So suppose 06 is written there, so it will move into accumulator and the content of accumulator will become 06. Now the fourth addressing mode is the indirect address, register indirect addressing mode. In the register indirect addressing mode, the content of the register acts as the memory location. It is register indirect. So if we write like move a comma at the rate R0, that means if here we have R0 and here it is written like 05, and then we have a RAM, and at RAM we have a memory location this 05, and say here it is written as 01, and here we have a accumulator. So it is saying whatever the content of the R0 at that memory location, whatever data is there, move that data into the accumulator. So the content of the accumulator will become 1. So in this case, in register indirect mode, the content of any register becomes the memory location, and the data residing at that particular memory location will move into the accumulator. Then we have in indexed addressing mode. Number 5 is the indexed addressing mode. This indexed addressing mode is used to access the data of ROM locations. Okay, so suppose we have some memory location, and we have ROM location or the program memory or the data memory, and some data is residing at ROM location 400. Then in that case, this index addressing mode will be used. So there are famously two commands which are used for index addressing mode. One is move C, and its content is A plus @ of A plus dptr. If you remember, we learned like dptr is the data pointer register, and it's a 16-bit register. So our external memory or internal memory can go for up to 64 kilobyte. So that is why this dptr has to be a 16-bit register, because it has to access 64 kilobyte memory. So it says whatever the content of the dptr, add to that the content of accumulator, and the resulting content is there at that memory location. Whatever the content is there, move that content into the accumulator. So say if we have a accumulator n has 0 0, and we have a dptr address is there, and suppose dptr address contains 400. So at that address, 400 plus 0 equals to 400. So at 400 memory location, whatever is written, move that into the accumulator. So the next content of the accumulator will be changed to 0 1. So this is how indexed addressing mode is work. Similarly, there is another instruction to access the external memory. It is used for the code memory or the on chip memory. But suppose you have connected external memory, then move x command is there, and that move x particular command is used to access the external ROM location address. Okay, so these were all the addressing modes which are supported by the 8051 microcontroller. Now we will move to another thing, a kind of instructions, or what are various kind of instructions are there in 8051 microcontroller. So 8051 microcontroller supports a wide varieties of range of instructions. So number first, we have arithmetic operations like arithmetic. So you can go through any book like Mazidi or any other book to exactly know how many machine cycles or how many bytes any instruction takes. So if we talk about arithmetic operations, so we have add, subtract, and now say if we have add, then add could be a comma register. So its first operand needs to be the accumulator, and the second operand could be any register. Similarly, SUBB command is there to subtract. In the subtract command, first operand needs to be accumulator, and the second operand could be any other register as well. Similarly, we have multiply and a division command, and then INC for increment, DEC for decrement, MUL for multiply, DIV for division. So in multiply, its syntax is fixed, it is A and B. Similarly, other kind of instructions are logical instructions. So arithmetic used some like addition, subtraction. Logical means greater than, less than, equals to. So we have and, logical or clear. If we want to clear the content of any register, we have complement. Suppose 1 is there, so it's after complement command it will change to 0. Similarly, we have RLC, rotate left through. Okay, before RLC we have RL, that is rotate left. Rotate left means we have our data 8. So in the rotate left, the content of this last byte will move here and all the bits will shift one location left. So this is rotate left. And rotate left through carry, and in rotate left through carry we have the content, 8-bit content, and the carry. So the last 8 byte, the last bit will go into the carry, and whatever the content of carry will go into the first location, and all the bits will shift one towards left. So this is rotate left through carry. Similarly, we have rotate right. So it's just the opposite of this one. The first content will go back and all the bits will shift it to the right side. Similarly, RRC, rotate right through carry. Same case, just opposite to this RLC. Similarly, we have, these were the logical operations. We have several other commands like data transfer, and these are one of the most commonly used instructions. Data transfer means we move data from one memory locations to the other memory locations. So most of the famous operation is move. So it transfer any register to any other register. Similarly, as we just discussed, move C to a ROM location and move X for external memory. Other than that, we have some of the memory location like XCH. This XCH is used for exchange purpose, so the content of the two registers are exchanged. Now there are two more instructions commonly used, and we just discussed in our last class: push and pop. Push and pop. So we discussed like how this instruction push and pop work. So these are instructions used for the stack to store the data onto the stack. So suppose we have, this is the stack and the content of the stack pointer is by default 0.707. So when we write like push 01, so the RAM memory location content of the memory location 01, suppose here it is 5. So how it happens, it first increment the SP by +1. That means now after this push instruction, content of SP will be 08, and then store the RAM location data of 01 to here. So it stores here 01. Similarly, pop, what pops to? Pop 01. So whatever the content of the SP at that particular location, whatever data is there, it transfers the data to the RAM location specified by this, and then decrement the stack pointer address by 1. So this is how this data transfer operation takes place. Now there are most commonly used branching instructions. Branch instructions. Branch instructions have very important significance. Suppose this is your code and the normal logic flow of the code is it keeps on one instruction by one instruction. And remember, we discussed like PC store the next instruction to be executed. So branch means if next PC is here, a next instruction to be executed here, but it transfers the control of the program to some other location, and it starts executing the instructions at that particular location and then comes back here. So these are known as the branch instructions. So they could be like, if you remember, you have must have studied about functions in C language. So there are two kinds of branch instructions. So this branch instruction can like a call instructions and the jump instruction. So you can think of these call instructions as functions in C. If, you may have gone through them. So what we do in functions? In functions, when a specific operation is repeating several times, so we make a small program for that outside of the main, and we call it and then get returned back. In jump, it tells like, okay, jump to the next location. So we'll just discuss these two one by one because the operation is different. So when we talk about call instruction, so there are two type of call instruction, A call and L call. So A call is known as the absolute call and L call is known as the long call, right? So in this A call, absolute call, if your program counter is this one, so it can go within the 2 kilobyte memory of the data. That means whatever the current address is there, it go within the 2 kilobyte addresses, up or down. That means can go above 1 kilobyte and lower 1 kilobyte. That means address is 1024. That means it could go here up to 00 and here up to 2048 memory location. So this is a condition on A call. While this L call stands for long call, and our memory or the code memory is up to 64 kilobytes. So by this L call, we can transfer the control to any location within the 64 kilobyte of memory. So this is the difference between these L call and A call. This is the 3-byte instruction and this is a 2-byte instruction. That is the difference, and we generally use for saving the memory because L call use one memory less than that of the L call, because when we write an embedded system, each memory is very crucial. So now this was the difference about L call and A call. Now what is happening in that case? In that case, now we have written our main program here. This is our main program, and we have making a subroutine. So in this case, in assembly language, it is known as the subroutine. So we have make a subroutine here. So what will happen in that case? Suppose, and we have used A call instruction here. So when this A call instruction will be executed by the computer, our content of the program counter will be the next instruction to be executed. Now at this A call instruction, control needs to go there. That means this particular address needs to be fed into the program counter. So the current address of the program counter needs to be stored somewhere. So what computer do? Computer store the current address of the program counter to the stack and then load the next address to the program counter. So now program counter starts pointing here, and our computer or the control start executing the instructions from there here onwards. and at the end there is a return instruction. In return instruction, whatever the content is stored, address is stored on the stack pointer, that loaded back into the program counter, and now the program counter start pointing this particular address and executing instructions here onwards. So it may be a little confusing to you, so let's repeat it again. In a call, the next address or the content of the program counter first stored on the stack pointer, and the next address which is pointed by the a call is loaded into the program counter, and then program counter starts executing the addresses of the instructions of the subroutine, and at the return instruction, again whatever the data was stored on the stack, that is fetched back and stored into the program counter, and then program counter again start pointing the next instruction from where it jumped back last time and start executing the normal routine. So this is the functioning of this jump routine, and that is why this is known as a branch. We are creating a branch from the main program. Similarly, there is another instruction which are used for jump, that is jump instruction. These also create a jump, but in this case address is not stored on the stack. So there are three type of jump instruction: SJMP, short jump. So this is within the plus minus 128 bytes. That is, this is, suppose this is the present location of the program counter, so it can go up to 128 byte, 127 byte here and 128 bytes here. Short jump. Then AJMP, absolute jump. Again, this particular jumps within the range of 2 kilobyte. Range of 2 kilobyte means the total range from starting to end where it can jump from present location. And then long jump, LJMP. So this long jump can be within the 64 kilobyte memory. So in this LJMP, suppose this is a main program and this is a program counter, and jump instruction is here to denote the address of this. So what will happen will be, whatever the address is there, that will go into the program counter, and then program counter will start denoting the instruction from where our next instruction needs to be executed. So this is how these jump instructions work. Now there are several kind of jump instructions. These were the normal jump. There are also conditional jump instruction. Conditional jump instruction like CJ and A. So it is, say, compare and jump if not equal. So we have, suppose, A, any data, and then address. So if these two data are not equal, then jump to this address. Similarly, we have most famous instruction D, J and Z. It says R0, suppose, and the address. So what is do? It decrement the content of the register. It could be R0, R1, R2, and when if this content is not 0, then it jumps to the address denoted by this second operand. So this particular command is used for providing a delay in 8051 microcontroller through programming language. So we will learn about these programs in next upcoming section. So I hope, and one of the normal instruction is NOP, no operation. This instruction do nothing and just consume the one machine cycle of the microcontroller. So in this particular, let's recall, in this particular lessons we have talked about basics of assembly and then various addressing mode and the instructions supported by the 8051 microcontroller. So in next lesson, most probably we start our first program in assembly, and some of the programs we will write and see how those programs are working in on a keel simulator. So I hope that's it for, I hope you understand, and that's it for this video. Thank you.